There is a lot of noise on the audio.
Maybe we can try muting all the participants. That works. Perfect. I see people have joined the meeting. It's 12 o'clock, so I would suggest to get started. Hello, everyone. This is today another session for the Brightland Young Professionals. Today we will discuss and talk about tire pyrolysis and advance on recycled carbon black. And we will have Black Bear and Ad van Oorschot as our guest speaker for today. I hope you can see my slide. Today I will be the moderator, Raffaele Bernardo, working for Arlanxeo as product development specialist. So the agenda of today, you can see that on the slide. So we will start with safety and a small introduction, and then basically we will give the floor to our guest Ad. There will be a small session for question and answers. Of course, if you have questions, I invite you to put them on the chat panel of the team meeting. We will save them for later, but of course, everything is encouraged to be asked after the presentation. Safety, some of you are on the campus. Majority, unfortunately, we have to stay home due to the pandemic, so everything has to be online. But for those of you in the campus, I would invite you to follow the safety procedures of the campus. So driving 30 kilometers, no smoking, alcohol not allowed, use mouth mask in closed areas, siren alarm in the campus. On the Brightland side, you are on siren area 22, so move to the gas light shelters. And in the event of the evacuation, follow the dedicated instruction towards the assembly point. And in terms of emergency, you just dial 5x6. Today, I'm introducing you Ad van Oorschot, Sales and R&D Director at Black Bear, who after finishing his chemical education, started in research and development, holding various positions up to group leadership. And then later in his career, he also finished an executive MBA and gave his career a commercial twist. So today he is going to talk us about carbon black and recycled carbon black and Black Bear, and we are really looking forward to hearing his presentation. Ad, the floor is yours. I will leave you the sharing the screen.
Raphael, first of all, thank you for having me here. I'm gonna try to put up my presentation. That might take a little while because it's a heavy, even quicker than I thought. Are you seeing the slides correctly?
Yes, perfectly.
Okay. I'm going to take you a little bit through Black Bear, what we do, why we do it, how we do it, and why sometimes we do it different than others. That is very nice. My agenda is to explain you a little bit about carbon black, because a lot of people will know carbon black even if they don't know carbon black. But also what are the typical properties and what are typical uses of carbon black. Then I'm going to tell you a little bit on end-of-life tires, why it is a problem and why we are focusing on reusing these end-of-life tires, a little bit on how we do it, and then in which applications we can or cannot really work. And then I'm gonna stop with a little summary. So that should take us probably 1 hour further. Anyway, carbon black. If you look at Wikipedia, carbon black is a material that is produced from incomplete combustion of heavy petroleum products. And there are several grades and they have several qualities. Some are also trying to use some vegetable oils, but that is not really sustainable because you will be burning a lot of vegetable oil before you can turn it into carbon black. And carbon black is a form of paracrystalline carbon. And that is why, although it is mainly made out of carbon, is considered to be an inorganic product rather than an organic product. And the fact that its melting point is about 3,500 degrees centigrade will have to do something with that as well. It has a high surface area to volume ratio. In other words, they are very small particles, and some of them have a very, very high surface area. It's not as high as of activated carbon, which we all know as NORID, for instance, and it is comparable but not the same as soot, in a way that there are considerable differences in surface to area ratios, and also the level of polycyclic aromatic hydrocarbons in soot is much higher than it is in carbon black. Carbon black is mainly used as a reinforcing filler in tires and other rubber products, but it's also used in plastics, paints, inks, toners, cosmetics, and giving color because of its high surface area. It also absorbs light very easily, and that is why it is so black. And even other black pigments like iron oxide will never give you the same blackness, the same darkness, the same jetness as that a carbon black will give you. Because it absorbs light easily, it's also used for UV protection, which is a secondary effect in tires. It provides the rubber from degrading under the influence of UV light. A carbon black factory is rather big, but where it really happens is, as you can see, rather small. These are the different components, and actually they are not so big. And I'm gonna switch to the next slide to show you a little bit what is happening inside that installation. What you have is a furnace in which you have a flame out of natural gas. But if you want to have a flame, you need some air. So there is an air supply. Then the heavy oil, which is fluid cracker condensate or coal tar or other heavy carbon oils, but they need to be fluid. They are injected into that flame. And that flame is very hot. It is 16 to 1800 degrees. And it basically atomizes the oil into carbon ions, but they are not very stable. So they directly convert into what they call the primary particles. So they start reacting, and that's why they form a paracrystalline structure. And you can imagine that the higher the temperature is, the smaller your primary particles will become, because that has to do with the surface tension and the surface energy. So the higher the temperature, the smaller your primary particle will be. And that is how you can make carbon blacks with different primary particle sizes. These primary particles are sticky, so they clog together and they build aggregates, so-called aggregates. And they do have an acino-grape-like structure. And you can determine and control the size of these aggregates by quenching in water. That water also contains an organic sodium salt. So the aggregates will repel each other. They will get an electrical charge. But later in the stadium, later in the process, these aggregates will form together agglomerates, and they are held together with van der Waals forces. And you can imagine that if you have a small aggregate with a very small primary particle, these van der Waals forces can be seriously high. So it will not always be easy to convert your agglomerates back into aggregates. And that's what you basically want to do when you disperse the carbon black. The reason that then a factory is so big is that you can imagine that if you produce carbon black at these elevated temperatures, it will take seriously time to cool down the aggregates and the carbon black. And that is why these factories have become so big, because eventually they are filtered out with bag filters to separate them from the pyrolysis gases. Because you can imagine that if you have a flame there and air, it's not just carbon black what you're making, but you're also burning some of the oil. So you will have SOXs, NOXs, COXs, which are in your pyrolysis gas. You will also get some uncontrolled carbon black formation. So there will be a minute amount of soot in your carbon black, and there will be some surface active groups, which are mostly phenolic, hydroxylic, carboxylic groups. And these two together is what they call the volatile content of carbon black. That means that the environmental impact of carbon black production is very high. It is very polluting and it is very energy consuming, because you have to bear in mind that to make 1,000 kilograms of carbon black, you need between 1,500 and 2,000 liters of oil. And the higher your temperature will be, the more oil you will need. You need about 5,000 liters water to produce 1,000 kilograms of carbon black, and that is to cool down, but also in a later phase to convert the powder into pellets in a process which they call wet pelletization. You need quite substantial amounts of natural gas for the flame to produce the flame. You will have electricity, although there is also recuperation from energy. But you can also produce up to 2,000 kilograms of CO2, making 1,000 kilos of carbon black, apart from some fine dust and NOx's and SOx's. So you need quite some energy to make carbon black. When it comes actually out either as a powder carbon black, which is also called fluffy. Many carbon blacks you can pelletize without using water, which they call a dry pelletized carbon black, or you can make a wet pelletized carbon black. So you add the carbon black to water and you turn it into pellets. And by determining the ratio between the water and the powder carbon black, you can determine the size, or you can control the size of these pellets. And they are usually between 1.5 and 2 millimeters, at least the wet pelletized. Delivery is usually in small bags, and that can be paper bags or low melting plastic bags. That can be in big bags, 500 kilo, 1,000 kilo. If you really have a big plant, you can also get it in containers, full truck or tanker loads, or railway loads. And depending upon the application, you can also have control over the pellet hardness by using binders. So now, where we know how carbon black is made, at least 98% of the carbon black, you can imagine that they have some properties. And these carbon black properties are determined by the fineness. So you can have either large primary particles, which will give you a relatively lower surface area, or you can have very small primary particles, and they can be as small as 8 to 10 micron. But that will determine the application and the use. The other property that we discussed was the structure, or the aggregate size or shape, but also the distribution, because you will nowhere make everything exactly the same size. So there will be a variation in the size of the primary particles and the size of your aggregates. And that is also why even an N330 from supplier A will not be identical to an N330 from supplier B, because they have a different way of producing the carbon black, which will mean that they will get a different primary particle size distribution, but also a difference in aggregate size distribution. So that's the reason why, even if they have the same colloidals or the same analytical properties, the effectivity of supplier A can be different compared to supplier B. And the other thing that comes into place is pore size or porosity, because you can have a relatively soft, smooth surface, or you can have a very uneven surface. And also the surface activity can be different, because you can have a lot of oxygen groups, or you can have less oxygen groups. And a lot of that is also determined by the configuration of your factory. So now you also know why even from the same supplier, if it comes from plant A, can be different in properties compared to plant B. That is, these are the main reasons for that. What is it used for? It's mainly used for two reasons. The first reason is that it's a reinforcing agent. So it bonds especially rubber polymers together and makes it more durable. So in rubber, it's mainly used as a reinforcement filler, but also sometimes for conductivity and for UV protection. In printing inks, it is used for pigmentation and rheology control. Because of the high surface area, there is a significant impact on viscosity. And that also determines why you can use certain grades in certain applications. And you cannot just pick a carbon black and put it in and make it to the properties that you are looking for. You have to carefully select your type of carbon black. In coatings, it's also used for black and gray pigmentation and tinting. In plastics and fiber, also pigmentation, tinting, but also UV protection, conductivity, or conductor coating or non-conductivity. Paper, same reasons. Construction, it's used for pigmentation in cement and concrete. It's used in carbon brushes, electrodes, battery cells. It's used as a metal reduction. It's a source of carbon, so it helps you melt metals. It's used as a friction reduction compound, carbon source. It's used in fireproofing because it's a reduction of mineral porosity, but it also absorbs heat and temperature, and that's why it's also used in insulation. Just looking at some facts and some figures, it looks like what it sounds like it would like. So yes, it is black. And despite the similarities between carbon black and soot, it is not soot. It is a industrial product made under controlled conditions, and soot is not made under controlled condition, and that makes it very different. So if you try to use soot to reinforce a rubber or tire, that will be a serious problem. In 2019, there was about 14.2 kilometric tons produced, which is more or less equivalent to 35 to 40,000 completely filled Olympic swimming pools. And the average growth rate is an estimated 5.6%. Due to COVID, that has been a little bit lower over the last year, but at the moment it is really recovering quite dramatically and drastically. Just over 70% of that capacity is used in tires. If you do not use carbon black in your tire to make it more durable, it will not last even 1,000 kilometers, but most likely it would catch fire before reaching that point. Another 20% is used in other rubber applications and 10% in specialties. And specialties is mainly plastics, because there's a lot of black, gray plastics going around in your life. 3% in inks, and that number is so high because of newspaper inks and packaging inks. And only 2% is going into coatings and many other applications. That number is increasing to the sheer fact that a lot of it is used in batteries, and with an increase in electric cars, electronic vehicles, the amount of carbon black will increase. Having said that, we now know that more than 70% of all carbon black produced is used in tires, but they come to an end. And end-of-life tires are not as, they keep you safe in your car, but they are not as harmless as they seem to be. Because a car tire is built to last, and it will last. If I do not do anything with a car tire, it will last for 80 up to 100 years. And even then you don't see it anymore, but it's still present in the form of microplastics. The second big problem with end-of-life tires is you have to keep them somewhere. And they will not catch fire easily. But once they catch fire, you're in serious trouble because it is almost impossible to extinguish the fire, because as soon as you stop as soon as you stop, how do you call it? If you stop extinguishing the fire, it will recatch fire because the heat absorbance of the carbon black in the tire, and there's up to 25–30% of carbon black in the tire, it will keep the heat inside and the fire will start again. There have been people, for instance, in Wales, and they thought to be clever, because it's also not a pretty sight, such a car tire dump. They stored it in old mine shafts. Unfortunately, that caught fire, and that fire burned for over 10 years, and they couldn't get it out. They couldn't get close enough to put it out because the heat was so extreme that the only thing they could do is to have it completely burn until all energy was gone. But it burned for almost 10 years. And the third biggest problem is it doesn't matter how you store a tire, it will catch water inside. And that means it's an excellent breeding place for mosquitoes. And despite COVID, the World Health Organization estimates that between 750,000 and 1 million people die every year because of mosquito bite related diseases. So what you also will see in Middle Europe, where we are, you see more outbreaks of tropical diseases. And an important source of that is end-of-life tires. They come into the country, and very often you will see that an outbreak of these diseases is usually in the area of 5 to 10 kilometer area from a car tire dump. So be aware. On the other hand, tire collection rates are high, and tire production worldwide is extremely big, but of 20.1 metric tons every year, 26 metric tons are taken back and are collected. So they do not just disappear into nature. And that has to do with illegal dumping or importation regulations. But there are some historical stockpiles, and we all know the tire fire we had in Madrid some years ago, but there's many more. ELT, end-of-life tires, collection and processing systems. Every country has a slightly different regulation, but it is regulated. And the reuse of end-of-life tires is generally split in two groups, as energy recovery, for instance, at cement kilns or paper mills, it is used, and then you just use the high energy and you just burn the tire as a secondary fuel. But what is more important and what is more attractive and is gaining a lot of traction is material recovery, and that goes from artificial turf fill-ins to regrinding and low-grade rubber application, but also what Black Bear is doing, carbon black extraction and pyrolysis oil extraction. and that is where Black Bear comes in. As already mentioned, there is a lot of tires recovered. And the environmental impact is, as discussed, very important. You can read the slides. I'm not just going to read out the slides to you, but it also helps to reduce health hazards. But also it's a reuse of existing materials, so against a waste of natural resources. There's other things you can do with the oil than to burn it to make carbon black. And what we do is we have developed a continuous process that allows the production of a high quality recovered carbon black, and which meets most of the specifications that manufacturers have throughout different industries where they are using carbon black. And what our ultimate goal is, but we still have a long way to go, is closing the loop by extracting recovered carbon black from end-of-life tires and make that available to reuse in tires. Because at the moment, most of the recovered carbon black that is on the market contains also substantial amounts of non-carbon black, which is basically mainly coming from the zinc oxide and the silica used in tires. And as long as you keep that in your recovered carbon black, you cannot fully close that loop, because you will be increasing the amount of especially zinc and silica in the tire, which will increase the, or better said, will decrease the recovered carbon black in your recovered carbon black. And that's still a problem that we know it can be solved, but it's easier said than done. So what we basically do to contribute to a sustainable solution is that we recover carbon black, oil and gas. And there is several grades of, or several levels in waste handling. And the lowest one is just to dispose of it and use it as a landfill or illegal dumping. And that is really not what you want to do. Then there is recovery. You can use it as an energy source. You can make tire-derived oil out of it. And you can do that in a batch process. We do it preferably in a continuous process. But you can also convert gas, the pyrolysis gas. We do it inert under nitrogen. You can use that pyrolysis gas to convert it into electricity and use the heat, for instance, for drying your pellets. So that is a part recovery, that is a part which Black Bear is doing. The other one would be recycling. So you have material recovery. You do that through granulation of tires, and you can use it as artificial turf or reclaimed rubber. But what we do is we take the steel out of it, and that can be reprocessed. At the moment, we do not do that ourselves, and we buy the granulated material. But there is no objection in doing it yourself. So you take in the tires, you get your gate fee, and you process it yourself into granulates, and you recover the steel and part of the textile. Then you go to reuse, and that is what we do. The tire-derived oil is being processed and reused as a marine fuel, and the carbon black that comes out it is processed and can be reused in rubber production. But we have made some advances that we can also use it or reuse it in specialty applications, which is what most of our competitors do not do or cannot do. And the highest level in the hierarchy of waste is to prevent the use of the product. And it says there is no alternative for tires and carbon black. Well, yes, there is no real alternative to tires. There is an alternative for carbon black, and that would be precipitated or fumed silica. But that has the same or similar problems to carbon black. So that's you solve one problem, creating another problem. So that's also not really what you want to do. What we do is we take whole tires. They are being granulated into granules which are below 25 millimeters. And the steel and part of the fiber is recovered and reused. Then it goes through our process, and from these chip tires, we recover about 40% as recovered carbon black, 45% of oil, and about 15% of gas. And that gas is converted into electricity through a CHP. And basically, it's a closed process. So you have a conversion to any of these three of almost 99.99%. So there is only very small losses. And with that, we are trying to close the loop. So we take waste tires, they are being processed through our factory. We manufacture recovered carbon black, and it's going back into tires. And a black bear process starts with the granulates, which are 25 millimeter and smaller, and they go into a rotary kiln at about 700 degrees. And we do that at such high temperatures because basically you can pyrolyze the tires at 450 degrees, 425, 450 degrees, unless you use a catalyst, but that will increase increase the ash content in your recovered carbon black. And we do it at 700 degrees because next to oil, you also get polycyclic aromatic hydrocarbons. They will end up in your oil, but more so, they will also polymerize and form soot. And as I mentioned before, that is an uncontrolled substance, so you want the soot content as low as possible. And that is why we are doing it at about 700 degrees, which usually means that we are at about 1.5% of soot in our end product, which will come out as volatile if you do a TGA. From that first kiln, it's going into a second kiln, and the reason for that is you have a very dense atmosphere in your first kiln, and it contains polycyclic aromatic hydrocarbons. Sorry. Next to that soot formation, it will also be absorbed by your carbon black because carbon black is a very good absorbent. And that's why we put it into a second rotary kiln where all absorbed polycyclic aromatic hydrocarbons and other more or less volatile organic compounds are removed from the recovered carbon black. And that is how we get to very low levels of PAHs in our carbon black. And in fact, they are EU 10 2011 food compliant. The next step that we go to is it's going into an intermediate hopper, and it is milled on a jet mill. And the reason that we are using a jet mill is twofold. First of all, it is able to make a much finer product than that you would get using mechanical grinding. So basically, most products do have a D99 of 17 to 20 micron. We are generally below 3 micron. And the second advantage is if you are using end-of-life tires, there will be sand and pieces of rock and stone and glass in it. And if you mechanically grind it, that will end up in your carbon black. And we have seen competitors' product that has a crystalline silica content of up to 2%. And we, although we have silica from the process that is used in the process to make a tire in our carbon black, but that's a precipitated or a fumed silica, we have no crystalline silica in our carbon black. And also smaller pieces of metal or other contaminants which are hard, they are taking out in that milling process. They end up at the bottom of the jet mill and it's been extracted and removed. After that, it's being processed as a conventional carbon black and it's pelletized and dried, unless for specific specialty customers who require the powder or use the powder, the fluffy, that can be bagged separately and shipped to customers. But otherwise, it's pelletized and packed, and that can be paper bags, EVA bags, 500 kilo big bags, or 1,000 kilo big bags. So as mentioned, our inputs are end-of-life tires. And we are using a single source tire granulate, which means that we do a pre-selection of tires. And the reason for that is if you have a high silica passenger car tire or a low silica passenger car tire, or you have a truck tire, or you have a agricultural tire, or you have a solid tire, or you have an off-the-road tire, they will differ from each other because they are built to different specifications, which means they will use different types of carbon black. But if you are using just, for instance, low silica passenger car tires, you only have a very limited selection of carbon blacks that you can use in that tire. And because you are using the same source and you are mixing them before and during pyrolysis, your output is very consistent, especially on your ash content, which is the non-carbon black part. That also means that you get very good color consistency, but also performance in rubber. Some of our competitors have, for instance, an ash specification, which is between 14 and 20%. And that is very high. If you have 14% ash, that will give you different results as when you have 20% ash. And we have a specification that is plus or minus 0.5%. So that is much tighter. As mentioned, tires are shredded and granulated, and that can be done either externally, so you buy the shreds, or you do it as a pre-processing part in your plant. Steel fibers are being removed. Our plant pyrolysis capacity is 45 to 50 kilotons of whole tires, a little bit depending upon the type of tire. And that's about equivalent to about 30 kilotons of granulate per year. And as mentioned, we do pre-processing of that feedstock to guarantee a consistent supply. Output, the gas stream from the pyrolysis process is cooled down. So in the kilns, the rubber is heated, evaporated, thermally cracked. So everything that's organic leaves the kiln as a vapor. That vapor is then cooled down and results in pyrolysis oil and a light gas, the so-called pyrolysis gas. The tire pyrolysis oil is cleaned, distilled into a light fraction and a heavy fraction and sold as a marine fuel blend component and gasoline booster. We are also looking in a process to use the heavy fraction to make carbon black, virgin carbon black. So then it's made from a sustainable oil source, or at least environmentally friendly recovered source. And the gas is burned and either used at our site or it's been sold back into the grid, electricity grid. Just to give you an idea, and why one quality is different as another quality. I already mentioned that we grind it down to very fine particles. And if you compare it in a rubber grade, we made some disper grade samples and had a look at them, then the level of dispersion that we achieve with our recovered carbon black on a macro level would be between an N550 and an N660. The only thing, if you have a closer look, that you can see is that on a micro level, we are still not quite yet there. And that is one of the reasons, not the only reason, but one of the reasons that the reinforcement properties of a recovered carbon black will be different compared to a virgin carbon black. And the second thing that you can observe is that if you have a product that is not milled or hardly milled, you will get a very poor quality dispersion, which also will result in bad reinforcing properties, but even more so in bad tear resistance and crack resistance. Having that mentioned, and I mentioned it earlier on, carbon black is mainly used for two major reasons. It's got a relatively very large surface area that absorbs light, and heat is a special form of light. That is why a black car is much warmer in summer inside than a white car. That also makes it an excellent black pigment, and the higher the light absorption, the jetter, or the darker, the blacker your carbon black will become. So if you have a black car, they are using very, very high surface area blacks. They have one disadvantage. They disperse very poorly. So if you have an FW to 100, which is the standard grade in automotive coatings, it's not uncommon that they have to disperse it for 48 hours to get sufficient grind fineness to get the darkness that you want. And now you know why such coatings are so expensive. It also has a large surface area, and that surface area has surface active groups. So you can imagine that the higher your surface area, the more surface active groups you have. And that is one of the reasons that a high surface area carbon black will give you better reinforcement than a large surface area carbon black. It also will be dependent on your level of dispersion, and that's where your structure comes in. If somebody wants more reinforcement, it's not always necessary to go to a higher surface area carbon black. You can also go to an easier dispersible carbon black, which will give you a better level of dispersion, which will also then result in better reinforcement or better jetness. I will never make that claim, but we have had some coating manufacturers that said that our grade was of a comparable jetness compared to an FW200, which from a theoretical point of view is impossible. Only if they do not disperse that FW200 sufficiently, that will cause the result that they got. So there is a very good reason to select very carefully the type of carbon black that you need for the application that you are looking for. There is a reason that there are so many grades of carbon black. So looking at that in more specifically, carbon black, I already mentioned, it's used in inks. It is used in coatings to make black coatings. It's used in tires. It's used in other rubber products. It's used in leather coatings. It's used in shoe polishes. It's used in textile yarns and fibers to make t-shirts, upholstery in cars, leather coatings, etc. It's used in plastics, but it's also used in some application areas that you would be surprised of that it's being used. It's used as a metal reduction. It's a carbon source to make metals pure. It's used in batteries, in electrodes. So that application area will grow. Because of all the electronic vehicles. It's used in refractory, it's used in bricks, it's used in tiles, it's used in electronics. If you have a very pure carbon black, it's very conductive. It's used in friction linings. It's used in cosmetics, although there are only very limited a number of carbon blacks that you can actually use in cosmetics, but it's used in cosmetics. So, and I'm seeing that I'm getting through my time. So, quick summary. There are many application areas in which carbon black is used, as discussed, and it's a fast-growing market. End-of-life tires are a problem to the world, and we need to find ways of doing something with these end-of-life tires. And Black Bear is playing a role in that, in the sense that we are able to make recovered carbon blacks that are used in coatings, and not just very simple coatings, but also high-end coatings. It can be used, and it's approved in inks. It's approved in some offsettings for food contact. It's approved for packaging inks, flexographic inks. But it's also used in cement application. It's approved in many rubber applications. It's approved in a number of tire applications. The thing which we are also doing is recovered carbon black is a new grade of carbon black. It is supplementary to existing virgin blacks, but because of its composition, because of the process it has undergone, it is an alternative type of carbon black rather than a replacement of existing carbon blacks. And it is certainly not just a cheap replacement. A lot of activities in the early 70s and 80s have done us no good by offering it unmilled as a char, as an alternative to carbon black at very low prices. That has not been very helpful. Therefore, because of the pure nature, it is not a one-to-one exchange or drop-in for existing blacks. It is a blend of 8 to 10 different types of carbon black. Thus, if you are comparing it to virgin black, it inherently will have different application properties. We also know by some experiments that we have done, if you really use it as an alternative grade of carbon black, in some application, it can give you better results than with a virgin carbon black. It's got a wide aggregate size distribution. In essence, it has the potency to give you better mechanical properties and keeping the same dynamical properties in a tire. So it can be a replacement for silica used in high silica passenger car tires. Unfortunately, also sometimes will give you worse results, because one of the things is the color, or better said, the tinting strength will be lower compared to virgin carbon blacks. Also, because of the pyrolysis treatment, the surface activity is different. I mentioned before, during pyrolysis, you also form some soot. In recovered carbon black world, they are called carbonaceous deposits. They surface on the surface area of your carbon black, and thus incapacitating the carbon black to give you reinforcement, which is a second reason that the reinforcing properties of recovered carbon black are different. So you need to optimize your level in formulations that you are using it. Recovered carbon blacks usually are not conductive because of these carbonaceous deposits on the one hand, because they are not conductive, and because of the high ash. Because we do the pyrolysis at high temperatures, zinc oxide is converted into zinc oxide, zinc sulfide that crystallizes, and that usually crystallizes at an active part of your carbon black, and it builds up. And the advantage is it also encapsulates the cobalt and lead which are in the ash, making it very difficult to extract out of your recovered carbon black. But we are doing ongoing research and developments to modify the surface activity and to make them free, or at least low in organics or low in ash content. One of the ways of doing it, and I saw that Vitaly is also here. He has a process to reduce the ash content significantly, and we also know by experience you can get as low as 0.5% in ash content using something like subcritical water extraction. But building that into your line comes at a cost, and we are already struggling with costs, so it's not so easy to do that. Also, what we do, pre-selection of tires, or even parts of tires. One easy access for a part of the tire would be retreaders of truck tires, and they shave off the old tread and replace it by a new tread. using that, you can develop and use that as a different grade of carbon black. But also it can be milled to different sizes, and that will also give you the opportunity to make different grades and more adapt to the different applications, but also save cost. I mean, it is energy consuming to run a jet mill, and if you mill it very fine, your throughput will go down. So there are still areas where you can optimize performance versus cost. And that is basically the things that are ongoing and that we are doing. So happy to answer any questions.
Thank you very much, Ad. It was a beautiful presentation. It also enabled us to get knowledge with carbon black and gave us all the tools also to understand a bit better what is done by carbon black in the second part. I see many questions. The majority they are on the panel. I see one person who has raised the hand, Michelle Mays. I would like you to encourage to unmute yourself, and then you can ask your question. Otherwise, I will start reading all the other ones in the chat panel. Okay, so I start directly reading the ones in the chat panel. I have one question from Alvaro Torres. So, dear Ad, you mentioned that your ultimate goal is to close the loop and be able to use recycled carbon black to produce new tires. In your opinion, how long will it take to develop the technology to this point? What are the elements and conditions you would like to from Brightlands Camelot to support you there?
That is a quite difficult question because it will very much also depend upon how soon this market will evolve and develop. Because research like that will cost money. And we do not have to think that we can overcome all these obstacles on a very short notice of time, just alone, given the fact that carbon black underwent a development of more than 100 years. So yes, I think we will get there. Yes, I think we will make great steps in the coming 10 years. If we will be there in 10 years, I am very doubtful about that.
Thank you. Then I have another question of Roybo. What would happen if you don't use carbon black in plastics? I think it's really wide.
Yeah, well, the only reason you are using carbon black in plastic is to make plastics black. In some cases, they will also give a little bit reinforcement, and you can get slightly better mechanical properties. But in most cases, you are not using more than 1 or 2% of carbon black to make a plastic black. Mm-hmm. So usually the concentration is so low that you will not see other effects than it just being black.
Thanks. I see another question from Niels van der Aar. So, did Black Bear review the LCA footprint of the various options with respect to the recovery, recycling, and reuse, as energy is required for the various options?
Yes, we have done 2 LCAs. We had a pilot plant in Nederweert, and we've done an LCA on that. And we now have developed a scale-up of the factory, which will be built in Gemelot. And we are comparing the gains in a second LCA comparing Nederweert with Gemelot. So yes, we've done an LCA, and you are saving substantial amounts of energy as well as raw materials. You don't need the oil which you need to make a virgin carbon black. So our grades that we make for color are called the Neptunes, and the NEP stands for net energy positive. So basically at a site at Gemelot, we will be producing energy rather than using energy. And that is because we are making that Tyre derived oil as well. And that has got a high biogenic content, over 50%, and it can be reused, and that gives you energy. So at the end of the day, we are producing energy rather than using energy.
Perfect. Thanks a lot. There is another question from Alvaro Torres. Are there positive technical properties from recycled carbon black that traditional carbon black does not have or perform less?
Sorry, can you repeat the question?
Yes. Are there positive technical properties from recycled carbon black that traditional carbon blacks do not have or perform less?
Yes, but then you have to look at it as a carbon black standing on its own. We know that if you are, well, most people will test recovered carbon black against an existing grade of carbon black. And that is not entirely fair, because you have a part which is not carbon black. What we have seen is if you increase the loading of the carbon black a little bit more, so you're using 10-12% extra, and you adapt your cure system so you will get a similar crosslink density or hardness, if you want to measure it easily. You will in generally find that you are improving mechanical properties and maintaining dynamic properties. And the reason for that is the wide aggregate size distribution. A company like Cabot has tried to bring wide aggregate size distribution carbon blacks to the market exactly for that reason. That is also the reason why a lot of people are using a mix of carbon blacks to get that optimized. With a recovered carbon black, you have that by nature. But because the surface activity is slightly different, and you still have the ash content, you have to adapt your formulation, which in most cases is not even a bad case, because the carbon black will be cheaper than your polymer.
Yeah, absolutely. Thanks a lot. I have another. Yes?
And just to give that answer, we do have some knowledge on that area, and we are happy to share the data and the information that we have with people that have an interest in that.
Perfect. Thanks a lot. We have another question from Philip Howe. Does the pyrolysis temperature influence the recycled carbon black particle size as temperature of furnace black production does?
There is very few things that will actively have an effect on particle and aggregate size. We are milling the carbon black, but we are milling it back into aggregates. I know of no mechanical way reducing aggregate size and primary particle size in a non-chemical way. And as long as you have no oxygen in your pyrolysis, not a lot will happen. What we see happen is, and we measure that by using XPS, Röntgen diffraction, that there is a strong indication that certain oxygen groups on the surface of the recovered carbon black are being replaced by sulfur and or nitrogen groups, because we are pyrolyzing at 700 degrees and nitrogen is an inert gas, but at 700 degrees it's not 100% inert. So we see some minor reactions.
Nice, thanks a lot. I have another question from Martin von Woldershoff. So do you have process capability data for maintaining plus minus 0.5% on the ash composition specs?
Yes, we do. And we know that by pre-selection of your tires and carefully treating them, we are actually even tighter. Usually we are plus minus 0.2, 0.3%. Okay. But our specification is 0.5% because every once in a while we notice that it's a little bit more than we observe in general.
Clear. Thanks. I have another question from Joseph George. What will be the approximate CO2 generation for 1,000 kilogram of recycled carbon black generated from end-of-life tires by pyrolysis compared to the normal carbon black production? So comparing to 2,000 kilogram of CO2 for every 1,000 kilogram of carbon black produced, as understood from the presentation. Yeah,
in that case, I would say, please send me an email because I do not know from the top of my head. It's of course our process is not completely without CO2 production, because if we convert the pyrolysis gas into electricity, and heat, some of it will convert into CO2, but it's my guesstimate is that it's at least 85%, if not 90% lower.
Wow. Thank you. I have one last question still from Philip Howe. Are there any national or international standards that describe the recycled carbon blacks?
There is an attempt going on, but it's a very complicated issue. And I know Martin is working on that very much together with the ASTM organization in the US, and there are already some standards. The difficulty is that every carbon black that is being recovered will differ from the competitor because the process inherently is different. Do or do they not pre-select the tires? Do they add other materials that they add in their pyrolysis? So some of them focus on oil production and they add plastics. It depends on how you will disperse it. It will depend on your pyrolysis temperature because it has an impact on the carbonaceous deposits, and it has an impact on the reinforcing properties. So it's being worked at, but it is a difficult subject and a difficult issue. I from the top of my head would not exactly know how you could distinguish and standardize recovered carbon black at the moment. Also, the fact that that a tire composition in the US is different than the tire composition in Europe will automatically also lead to a difference in recovered carbon black from Europe compared to the US. because they are using different types of carbon black. So that is a little bit difficult.
Clear. Thanks a lot. In the meanwhile, another question popped up in the chat panel. So it's from Bart Smiths. So you focus on carbon black, but what can you comment in general terms on the whole process economics? For instance, do you pay for the feedstock, and how is it important the fuel and electricity production compared to the carbon black value?
You can find that all in the LCA that we have available for people that are interested. Usually, the tire collection system will provide you, if you collect tires, that you will get a gate fee for these tires. So when you buy a tire, you automatically pay for the collection of the tire when it's come to its end of its life. And from that pot of money that then exists, the tire collectors are being paid. So if you would do your own granulation, yes, you could get a gate fee, which would be about 80-90 euros per ton. If you do not do that and you buy your granulates, then you pay a fee for that granulate because of all the energy and efficiency that they did put in. The carbon black we sell at almost comparable prices as virgin carbon blacks, because we do not see it as a cheap replacement. And the tire-derived oil is being sold and processed and is an income source as well, as can be the metal and the textile fibers that come out of it. So it's not just making money with your recovered carbon black, but there's other process steps that will also bring you money. Effectively, if you do it right, you operate it right, you should have an ERR of about 20 to 25%, depending a little bit how expensive the land is or how you lease it. I hope that answers the question.
I believe so. If not, we can hear. Yes, indeed. So it's answering the question. Thank you very much. I don't see any more questions in the chat panel. Maybe. No, not anymore. So one thing I can do, I can collect all the acknowledgements from the audience and for the nice answers and the nice presentation, get along with them. And thank you a lot, Ad, about your presentation. It was very nice. Also for all the answers that you provided. As a token of gratitude, the Young Professional Board of Brightland, we are going to facilitate the planting a tree on the Camelos campus with a plate recognizing, of course, the talk of today and Black Bear in a sense. And we will notify you once the tree has been planted, also with the nice pictures, and share some more details with that.
Thank you. And I will come and see how it grows myself, as we are planning to build our next plant on the Gemelot site. So
that's very nice. So we will be working neighbors then.
Yep.
Somehow.
Yeah.
So thanks a lot for the presentation again. Thanks everyone for attending to the nice meeting of today. As there are no more questions, I would like to close the session and greet you and wish all of you a very nice day ahead.
Well, I thank you for the invitation and showing your hospitality and have me to give a speech. And all the people that are still there, thank you for participating. Thank you.
Thanks a lot. Have a good day, everyone.
Same
Bye-bye.
to you.
Bye-bye.
Take care. Bye-bye.